With that, I hand over to Vishnu to Jejjala for the last talk of today. He's going to discuss aspects of Calabi-Yau geometry.
Thank you. First of all, I'd like to start by thanking the organizers. It's been a wonderful conference. I've learned quite a lot, so I'm very happy to be here and have an opportunity to speak here as well. So I want to tell you today about some aspects of Calabi-Yau geometry that I've been thinking about for the past couple of years with various students and collaborators. And we'll see how these aspects of Calabi-Yau geometry can eventually facilitate constructions of the real world. So the goal in string theory, the theory of everything from the 1980s and our bad PR days, was claiming that we could get a realistic construction of the physics we see every day from a fundamental theory. So so far, that objective has not been accomplished, as we all know, but we've come close in some ways, and we're still very far away in other ways. So to begin with, we would settle for a modestly unreal world rather than the real world itself. And by modestly unreal world, I mean a world with n=1 supersymmetry, a world with the gauge group that we see in the standard model, matter and the appropriate representations to the standard model, the appropriate interactions for this matter content that we've got, 3 copies of the matter replicated generations, and then some cosmology. So this is quite a laundry list of things we want to realize. Grocery list, maybe.
Sorry, but why do you want n=1 supersymmetry? I thought LHC was behind us.
Well, I said it's a modestly unreal world. It's not. I think we can, if we have the right or a reasonable n=1 supersymmetric construction, then we can think about soft breaking terms. And then if you realize the real world from this construction as a starting point. I'll be talking about Calabi-Yau compactifications. So the result of Calabi-Yau compactification on a threefold will be n=1 theory if we talk about hadronic construction. So that's the motivation as a starting point. This first half of this list has been accomplished in various constructions. This is consistent with cosmology part, has not been realized in any of these constructions of the standard model or a supersymmetric version thereof from string theory. What's also not realized is precise form of the interactions. So we have the right terms, we don't have a computation of electron mass, say, from a string model. So the program initiated by Candelas, Horowitz, Strominger, and Witten back in the day was that if we find the right Calabi-Yau, we can realize this entire list. It's often said that we're nowhere close, and it's often said that the goal's been achieved. Both of these statements are only half true, in the sense that there are now roughly 1,000 maybe hadronic constructions of the standard model with supersymmetry from string theory. What we don't have, of course, is particle masses in this construction. But the right terms, the right Yukawa terms for all the charged matter fields are present in these superpotentials. There's of course no reason to just restrict ourselves to hadronic model building. There are other proposals like pre-fermionic constructions, intersecting brane models, orbifold constructions, and whatnot that have been hypothesized as other paths to a more or less real world. So the Calabi-Yau compactifications have a natural home in the hadronic context, but of course that's not the only way, and we should so far keep our options open. So a Calabi-Yau, this is a fellow named Me has essentially shown us what K3 projected into 3 dimensions looks like. This is the manifold from various angles in this projection. And the same guy has looked at the quintic projected, and it's also very, very beautiful geometry that one can find. So these Calabi-Yau geometries that I'm going to discuss have certain mathematical properties that are conducive to constructions of n=1 theories in 4 dimensions. So the definition of Calabi-Yau is there's no vanishing holomorphic 3 form on a threefold, for example. And it's equivalent to saying the canonical bundle on this geometry is trivial, and it's equivalent to saying there's a Kähler metric global holonomy in SU3, for example. So these are what I'll be using as a definition of a Calabi-Yau. For compact Calabi-Yau spaces, there are other definitions one could use, which are slightly weaker than this. For example, the vanishing of the first Chern class. So I'll begin by discussing certain patterns in the distribution of known Calabi-Yaus. This is work I did with my student, Luca Pontiggia, who's in the audience back there. And then I'll discuss some other work I did on constructing a database of explicit Calabi-Yau geometries. And then within this database, we're going to search for a particular scenario for cosmological model building called a large volume scenario. And these large volume scenario means the volume of the Calabi-Yau is controlled by the volume of certain cycles in the geometry. And these are so-called Swiss cheese geometries, whose structure I'll try to make clear. And the number of large cycles that are present in these Calabi-Yau geometries tells us about the number of flat directions in low energy effective potential, and this may tell us how to engineer inflation in a semi-realistic string context. And then I'll discuss some prospects for how this program can proceed in the future. Okay, so I'm going to be restricting myself to a certain class of Calabi-Yau threefolds. These are called the Toric Calabi-Yaus. This is not the most, there are Calabi-Yau threefolds that are non-toric, so this is not the generic example. This is the example for which we've got the most data. So this makes sense to maybe begin here. And I'll remind you what a toric variety is, since I'll be talking about toric threefolds. So suppose we've got an equation that tells us the sum of the modulus squared of three complex numbers is 1. So this is a submanifold in C3. So suppose we then identify these numbers, Z1, Z2, and Z3, up to a phase. This gives us P2 in C3. Now, the original equation I wrote down can be written in terms of coordinates x, y, and z as x plus y plus z equals 1, which defines for us a triangle. This triangle I'll call B. Now, I've got three numbers, Z1, Z2, and Z3, so I can use this phase equivalence to set Z3 to be phases. So then, I use this U1 to choose the phase of Z3, but then the phases of Z1 and Z2 are free to be anything they like. So that gives us two S1s, which is a torus. So there's an algebraic torus in the game in this construction. Now, the Calabi-Yaus I'll talk about are similarly toric. There's an algebraic torus somewhere in the game. Okay, so these toric Calabi-Yau manifolds can be constructed by starting with what's called a reflexive polytope. A reflexive polytope is defined as a convex hull of finitely many lattice points, and inside there's a single point, which we'll call the origin. So starting from such a reflexive polytope in various dimensions, you can construct a Calabi-Yau in one lower complex dimension. So there's an algorithm for doing this. This algorithm was developed by these guys, Batchev and Borisov. So the reflexive polytopes, which you can construct Calabi-Yau threefolds of toric type, have been cataloged. So the guys who did this were Kreutzer and Skarka in Vienna, and this is a tour de force of computational power in the late 1990s, which led to this classification of 473,800,776 reflexive polytopes from which you can construct toric Calabi-Yau threefolds. We do not know how many Calabi-Yaus there are, as I'll try to make clear later on, but there are at least 30,108 Calabi-Yau threefolds, because that's the number of unique Hodge numbers in this database that Kreutzer and Skarka developed. So this is a plot of the Hodge numbers. This is the famous mirror symmetry plot that the Candelas and company used to show that there's a symmetry of the Hodge diamond for these Calabi-Yau threefolds. And we see that if you put a mirror here, the graph looks the same. And this is a plot of two Hodge numbers, H11 plus H12, versus the difference, H11 minus H12. So this distribution of polytopes has this obvious symmetry, this mirror symmetry, just by inspection. And we can ask whether there's more structure to this database that has been developed. So this is a contour plot of the same database. So here the colors represent how many of these half a billion polytopes have particular Hodge numbers in this list. So the peak of distribution turns out to be H11 and H12 are both 27, and there are roughly 1 million such polytopes. So one thing we get asked is, are there patterns in this database when we look at the number of Calabi-Yau polytopes with these Hodge numbers? So since I'm asking the question, the answer is obviously yes, there are such patterns. So here's a 3D plot of the number of polytopes with these given Hodge numbers. So this is the same mirror symmetry plot as before, except extended to 3 dimensions, where the third dimension tells you how many polytopes have these particular Hodge numbers. So if you eyeball it, you can sort of see there are curves that are interior to this distribution. And what Luca did was he looked at this database in this graphical form, and he fit these curves along various cross sections. So the first thing you notice is that the colors here represent even and odd values of these Hodge numbers, and you can see that the even points, which are in red, and the blue points, which are odd, follow different profiles. So that's the first thing you notice in this data set. And if you fix certain values of H11 plus H12 and ask what the distribution of H11 minus H12 with those fixed values are, you'll find that there's further structure. So what Luca again found was that if you take fixed values of H11 plus H12 and ask what the profile is in the H11 minus H12 direction, you'll find that the best fit curve follows what's called the pseudo-void distribution. The pseudo-void distribution is the sum of a Gaussian and a Cauchy distribution. And this is the best fit of all the test functions we played with to this date. Similarly, if you look at the cross-section where you keep H11 minus H12 fixed, and you look at the distribution of H11 plus H12, this number is going to be something positive, and we find the best fit to this is the Planck distribution. I don't have a good detailed understanding of where these distributions come from or why this data fits these distributions, but that's what we find. So it'd be nice if we have some detailed understanding of the profile for the entire three-dimensional function. We don't have that yet. Okay, so that's Luca and getting this work. So I want to now talk about starting from these polytopes and constructing actual Calabi-Yau geometries. So this is just a mathematical version of the statement I told you previously. We have lattice points, which are described by integer vectors, and these lattice points are reflexive when there's a single interior point within this polytope. And starting from this reflexive polytope, you can construct a Calabi-Yau hypersurface as toric using some polynomial equations. So starting from the polytope, we can triangulate in different ways. Each triangulation gives us a Calabi-Yau hypersurface, and sometimes these triangulations give us, in principle, the same hypersurface starting from different polytopes. And sometimes the same polytope, if you triangulate differently, will give you a different Calabi-Yau. So we don't know how many Calabi-Yaus there are either. We know that starting from one of these polytopes in a triangulation, you can form a Calabi-Yau. We don't know how many there are. So the triangulation is basically starting with a polytope, breaking it up into 0 simplices, 1 simplices, 2 simplices, 3 simplices, etc. And then the property of triangulation is the union of all the simplices which covers the polytope, and the intersection of any pair of simplices is a possibly empty common face. So from the triangulation, we construct what's called the Stanley-Reisner ring. So here's a sample triangulation. Here I've got 4 points, A, B, C, and D. A and B, B and C, and C and D are connected by lines, so 1 simplices. And the points AD, the points AC, and the points BD are unconnected. So this polytope here, this consists of the null set, the points A, B, C, and D, and the line segments A, B, B, C, and C, D. So there's an ideal which consists of the line segments, the 1 simplices, which are not represented in the polytope. That's AC, AD, and BD. So we take a polynomial ring in these variables A, B, C, and D, we mod out by this ideal. That gives us what's called the Stanley-Reisner ring. So what Bajrov and Borisov showed was that unique rings correspond to different Calabi-Yau geometries. So starting with triangulation is a prescription for constructing a Calabi-Yau. So for each of these Calabi-Yau geometries, we have topological data, like the Hodge numbers. We also have more detailed structure, more refined structure, the intersection forms, the Kähler cone, etc. And all of these will be meaningful when we start trying to do some constructions based on this data that we start out with.
So Vishnu?
Yeah.
By unique rings, you just mean if two triangulations give you the same ring, they're actually the same Calabi-Yau. Is that what you mean?
If some constraints on the intersection forms and Kähler cones also are the same. So this is a simplified version, but roughly speaking, yes. Okay, so as I've said, every triangulation gives a Calabi-Yau. We don't know how many Calabi-Yaus there are. Different triangulations of the same polytope can, in general, give different Calabi-Yau manifolds, but we don't know how that works either. So it's very difficult, because we don't know metrics, to map one Calabi-Yau geometry to another. So we know, for example, that all K3 geometries are diffeomorphic. We don't know that about manifolds, even if the Hodge numbers are the same. So without knowing that, we can't say that two Calabi-Yaus, even with the same topological properties, turn out to be the same geometry. We know that there are 16 polytopes in R2, which give rise to elliptic curves. These are Calabi-Yau one-folds. There are 4,319 polytopes in R3, which give rise to these K3 geometries. And Kodaira showed that all of these K3 geometries are diffeomorphic. And we have some number of Calabi-Yau geometries arising from this number of polytopes of toric type. And we don't know how many there are. There are at least 30,108. We don't know anything beyond that. Okay, so what these guys and I did, so Ross Altman was Brett Nelson's student at Northeastern, Young because of City University, and James Gray's at Virginia Tech. What we did was we started off with this database, the Toric Varieties, and we started to triangulate these geometries, these polytopes in various ways, and construct the explicit Calabi-Yaus out of these polytopes. And we started formulating a database of these Calabi-Yau geometries. Okay, so the database essentially provides Calabi-Yau data so far for values of H11 less than or equal to 6. So we've only started analyzing this. As I said, the database peaks at H11 equals 27. So we're rather far from the peak of the Calabi-Yaus we can construct, but computational limitations basically restrict us to looking at H11 less than or equal to 6. And so far, this is the number of Calabi-Yaus that populate our database. So this database is publicly available, and you can extract Calabi-Yau geometries from this database and do all sorts of model building. And it's sort of been a resource for the string community since we published this database. Okay, so we're going to look for particular types of Calabi-Yau geometries within this database, which will facilitate certain types of model building. So the database, the Hodge numbers basically describe what are called Kähler parameters and complex structure parameters. So Kähler parameters, roughly speaking, describe the size of the geometry, and complex structure parameters describe the shape of the geometry. So the simplest example is a torus. There's an A cycle and a B cycle of a torus. The A cycle, if you consider a solid torus, this A cycle curve is contractible, and the B cycle curve is the one which is orthogonal to it. So given this structure, this torus, we have two parameters. One basically describing the angle here, that's the shape parameter, and one that describes the volume, that's the size parameter. All of this stuff scales up to Calabi-Yau 3-folds and higher. Okay, so the moduli of Calabi-Yau are described by these Hodge numbers, H11 and H12. H12 counts the number of complex structure moduli, H11 counts the number of Kähler moduli. So again, this is size and this is shape. So there's a further modulus in the game, the axiodilaton, and we'll see what various models look like with this set of moduli. Okay, so these moduli H12 and H11, we're essentially counting 3 cycles and 2 cycles and 4 cycles respectively. So just like the torus had a hole in it, for Calabi-Yau 3-folds, we can have higher dimensional holes. That's what the 2 cycles, 4 cycles, and 3 cycles represent. Okay, so the moduli will turn out to be geometric properties of the vacuum, And there are lots of moduli for the typical Calabi-Yau. So we notice the peak happened at 2727. So the generic Calabi-Yau will have order 50 some moduli. In the low energy effective theory in 4 dimensions, these moduli will appear as massless scalars. So the number of moduli can yield essentially massless scalars in low energy effective action, and those massless scalars can be used for things like inflation. So that's the sort of story which I'll try to develop in the remainder of the talk. Now, left unstabilized, these moduli lead to fifth force effects, which you don't see, so there must be some stabilization mechanism. And the typical stabilization mechanism people use are flux stabilization in various types of constructions. Now, there may be problems with this, and I'll discuss that a bit later. I'll say a few words about that later anyhow. Okay, so I'm working in type 2B supergravity, and this is a Kähler potential with alpha prime cube corrections included. The condition for moduli stabilization for this class of models is that some parameter, which is related to the topological number of the Calabi-Yau, needs to be positive, which tells us the topological number chi is less than 0. This Euler characteristic is described by the difference between H12 and H11. So for the geometries we're looking at, there's strictly more complex structure moduli than Kähler moduli. Okay, superpotential of this theory is of Gutkopf-Vafa-Witten type. So there's this piece which is related to the holomorphic freeform wedge G3, and in addition, there are corrections which are related to these Kähler moduli, which I'm labeling Ti. So these prefactors depend upon the other moduli, the complex structure moduli, and the axiodilaton. Okay, so here's the notation. The notation is we're going to express the intersection form in terms of a divisor basis. These divisor bases basically let us encode how to capture the volume of our Calabi-Yau geometry. So this volume can be described either in terms of the Kähler structure or in terms of the holomorphic freeform. So if you integrate J wedge J wedge J, you integrate omega 3 wedge omega 3 bar, you'll get the volume of the geometry. And in terms of these two cycles, we can write the volume as some intersection number times 3 of these two cycles. Similarly, by taking derivatives of this volume, we can obtain volumes associated to these divisors, which correspond to 4 cycles, and volumes corresponding to the 2 cycles. We just take derivatives of the volume with respect to these Ti in order to find these things. So morally, the 4 cycle is constructed as a pair of 2 cycle volumes, and the 2 cycle volumes provide a basis for describing these structures. Okay, so the class of geometries we're going to look for are so-called Swiss cheese geometries. These Swiss cheese geometries have a volume which is dominated by a certain set of large cycles, and these small cycles we regard as holes in this geometry, hence the name Swiss cheese. So we have some volume, which is basically described by this large cycle, and these small cycles are subtracted out. So in a large volume scenario for string compactification, we usually work in type 2, and we look for a lifting which takes us from a supersymmetric vacuum to a vacuum which is de Sitter-like, which breaks supersymmetry naturally. Now this is unlike KKLT, in which you uplift to an ADS vacuum and then break that to a de Sitter vacuum. So the KKLT prescription is really a 2-step process, whereas this large volume scenario is a 1-step process to get a de Sitter-like vacuum. Now, there's some caveats here, and these caveats basically correspond to whether these models are consistent. And so far, we don't know. There are arguments that KKLT is these presence of fluxes basically describe the presence of anti-branes in the geometry, and these anti-branes lead to tachyonic modes, which may destabilize the setup. Since these large volume scenarios also rely on fluxes, they may be plagued by similar pathologies. So Bena and collaborators have argued that KKLT just doesn't work, but they haven't really looked at the large volume scenario yet. They haven't, but Joseph tells me that he suspects this is also problematic for similar reasons. There's another line of reasoning which stems from the weak gravity conjecture. So Vafa and Aguri argue that this whole setup with flux simplification really belongs in the so-called swampland and isn't realized in realistic string theory models because any of these flux compactifications will somehow lead to violations of this weak gravity conjecture, which asserts that gravity is the weakest force. So the arguments regarding the weak gravity conjecture, I think, are also, well, the arguments rely upon extremal black holes which are non-BPS being unstable. And it's not clear to me that that always happens. So I'm not sure about the status of the weak gravity conjecture itself. So given that it's a conjecture, we don't know whether this actually excludes this type of construction either. But tachyonic mode certainly would. So it's an open question whether this class of models needing to consider like vacua is the right procedure in order to recover a model which resembles our world.
One thing I don't fully understand about the open buffer argument is
yes.
If they have explicit SUSY breaking in mind only, or only explicit breaking in mind, or they also talk about spontaneous.
I think they've got explicit breaking in mind, but I don't know.
Yeah. To Ogure I have asked, and he said he also had spontaneous breaking in mind, but we didn't have time to discuss much, so I'm not really sure. If spontaneous breaking, can it be?
I don't know. I mean, from their paper, I thought they were talking about explicit breaking. But
That was my impression as well.
I think the more difficult question is whether the weak gravity conjecture actually applies. And I have reservations, or I don't misunderstandings maybe about that. It seems to me that if you have an extremal black hole, whether it's BPS or non-BPS, you really can't tell just by looking at physics localized near the horizon maybe. And the property of extremality is what gives you this ADS2 in the near horizon region. And that's the same independent of whether you're extremal or non-extremal, or whether you're BPS or non-BPS. So if the physics of black hole decay is mediated by Hawking radiation, that should be just physics associated to the near horizon region. And that's the same for extremal and non-extremal structures. BPS and non-BPS extremal structures. So as a result, I'm not sure why they insist that non-BPS extremal black holes must decay. And they need that in order to ensure that gravity is the weakest force. So I'm unsure about the status of the conjecture itself. Okay, so in any case, there may be arguments that this whole setup for flux compactification, in whatever guise, is unstable, and that's so far an open question. Okay, so in a large volume scenario, we're working on a limit where the volume of the Calabi-Yau is large, and we can expand then in a perturbation expansion about 1 over V. So in this perturbative scenario, we look at superpotential, which is described by the effects of the presence of these large and small cycles. And we find the Kähler potential has this form. And the mixing of the various moduli with each other is parametrically suppressed in this 1 over V expansion. So in this 1 over V expansion, you can compute the potential. And the potential ends up looking like this in terms of the inverse Kähler metric of the superpotential. And there are various competing terms in the potential. There's a 1 over V term, there's a 1 over V squared term, there's a 1 over V cubed term. But because of the presence of these other factors in this expression, all of these terms are the same order, and they compete. And in the limit where large cycles are much bigger than small cycles, we can express this potential in a particular form. And within this context, we can stabilize the moduli by demanding that the volume of the Calabi-Yau is given to us by the expression at the bottom. So this is a scenario that has been applied by mostly Quevedo and his collaborators in order to construct de Sitter-like vacua from string theory. Okay, so I'm being agnostic about what large volume means. Phenomenologically, there are several possibilities. The volume could correspond to a high string scale or a string scale just beyond the reach of current experiments, I'll call all of these large volume scenario. So far, we can't experimentally distinguish from any of these different options. The way we end up determining where the string scale is, or seeing where new physics centers in gravity, is by looking at small scale deviations from the expectation of a Cavendish type experiment. And that's only sensitive so far to scales of tens of microns. So beyond that, we can have large extra dimensions, and this scenario is not excluded by experiment. We have a prejudice that this is most probable that the string scale is relatively close to the Planck scale. But so far, the jury's out. Okay, so we've constructed a database of Calabi-Yau manifolds, starting with a Purchase-Skarka list and doing appropriate triangulations. Now we aim to determine which of the geometries within this database of Calabi-Yau geometries are Swiss cheese. And we can look for geometries with several large cycles. The number of large force cycles -1 gives us a number of flat directions, the low energy effective potential. And if, for example, there are 2 large cycles, we've got 1 flat direction, which we can maybe engineer in an inflationary context. And I'll discuss the inflation at the very end of the talk. Okay, so we initially tried to look for these Swiss cheese type geometries back in 2012. This is work I did with James Gray, Jan-Louis He, Benjamin Yerke, and Brent Nelson and Joan Simone. So back then, our idea was that we were looking for realizing these geometries by looking for explicit solutions with large volume of this particular form. The problem is that there are 2 different bases you work in. There's a basis of 4 cycles given by these taus, and the basis of 2 cycles given by these t's. So what's large in one basis being mixed up in the other basis, and disentangling how the 2 bases are constructed is the crux of the problem. So in terms of these scalar forms, we can express a scalar form either in a basis that accommodates large taus in a natural way or large t's in a natural way. And we need to invert expressions in going from one basis to another. In these geometries, we're working with small h11, but h12 can be large. So there could be lots of things to play with here, and it's often difficult to do these inversions. So we can solve the system explicitly when roughly the 4 cycles are squares of the volumes of the 2 cycles. But that's the scenario in which we had detailed control of these calculations in our prior work. Now, we're trying to solve things in a different way this time, which will be less general than what we did previously, but can facilitate finding more solutions readily. So that's the innovation in the last year or so. Okay, so the work with Ross Altman, Jan-Louis He, and Brent Nelson tries to be clever about how we do these things. So this A basis emphasizes large cycles that are 2 cycles, and this B basis is the same for 4 cycles. So within these bases, we can express various conditions for the intersection forms that describe how the cycles intersect. And we want a non-zero volume, so that gives us a certain set of conditions on these intersection forms. We want certain large cycles to exist, that gives us a certain other set of conditions. We want to make sure a small cycle exists, and that gives us a third set of conditions. And we have these rotation matrices that allow us to rotate the taus and the t's along each other. So that's the input into this calculation. And there's a special basis which descends from the divisors that we obtained from the triangulation of the reflexive polytope. And in these bases, we can express, in this particular basis, we can express these conditions for finding a large volume scenario combinatorially. So we do that, and we just put it in a computer, and we solve these combinatorial constraints, and we see how many solutions we construct. So that's the methodology. And there's some technical constraints. in terms of the Kähler metric and in terms of homogeneity, which is a simplifying assumption which is not required, but it helps us find solutions. So we implement this homogeneity condition, and there are various other technical conditions related to the Kähler cone to ensure the smoothness of our Calabi-Yau geometry. So we implement all of these conditions, and we find that this is the set of toric Calabi-Yau geometries that are Swiss cheese. So NL describes a number of large cycles. We found examples with 2 large cycles and 3 large cycles. In total, we constructed 2,268 new large volume solutions in this program. Now, there are complementary techniques. We relied mostly on intersection form. You can use other things to construct these solutions. And there was a paper last week by Chickoli and collaborators that used other techniques, and they found different solutions which are not in our database as well. So a combination of these techniques construct a bunch of new solutions. So in particular, 70 of these geometries have at least 2 large cycles. Okay, so this is a plot of the potential. Since the theory, okay, so these Swiss cheese solutions, by themselves are supersymmetric. So the potential has a minimum of 0, and we're looking basically from minus infinity to plot a log of the potential, and that's we isolate the fact that these minima exist as we claim. So the volume of the Calabi-Yau is expressed in terms of the volumes of the various cycles that are present, and here I've engineered things so that I've got 2 large cycles, and these 2 large cycles I'm taking to be the same size. So in different plots, I'm seeing the existence of this minimum as claimed. Now, the effective potential is written down here, and we can check that with the various reasonable assumptions for the parameters which appear in this expression, there is indeed a minimum with a large volume, and there's a parametrically small force cycle in the game, and there's a flat direction since there are 2 large cycles, and this flat direction is oriented in this manner. So this is an example in which this flat direction in the low energy effective theory may be used to engineer an inflationary model. Okay, so inflation. The number of flat directions effective potential lets us study inflation in this large volume scenario. The number of flat directions -1 counts the number of large cycles in the Calabi-Yau. And because we can only scan for small values of H11, we only have examples with 2 large cycles and 3 large cycles corresponding to 1 flat direction or 2 flat directions. So I'll look for how inflation behaves in examples of 1 inflaton field or 2 inflaton fields. So the data from the cosmology experiments, WMAP and Planck, strongly suggest that with 1 inflaton field, if you have a polynomial potential with the leading term of the polynomial quadratic or lower, quadratic or higher, such models have been excluded at 2 sigma or 3 sigma confidence. The leading exponent is less than 2 at that level of confidence. So these polynomial potentials with a single inflaton may not be the scenario that ultimately gets realized, even though the simplest scenario to teach an undergraduate cosmology course. The constraints are much less stringent when you add additional inflaton fields. So with 2 scalar fields, the polynomial potentials are, as far as I know, are just fine. Okay, so and we have explicit examples of this. So maybe this next bit of random landscape technology that I'll develop can be used in the study of these explicit examples. So far, I'm not going to look at the potentials I obtain from a Swiss cheese compactification with 2 or 3 large cycles, but a model will happen if we do that. So if we have a bunch of inflaton fields, the effective action governing inflation has the Einstein-Hilbert term plus terms involving these scalar fields. And I'm going to take the potential to be a polynomial in these various scalar fields. So I'm going to assume that inflation takes place at the scale corresponding to the gut. This is essentially to ensure that monopoles are inflated out. And I'll assume that higher order terms beyond the renormalizable level are suppressed by some higher energy scale, say the Planck scale. So that way I can truncate my effective potential at the renormalizable level. So I'm also going to assume the potential is bounded from below for obvious reasons. The mass terms of the inflaton will be at this gut scale, since that's the natural scale in the problem. Okay, so if we have a single field, I'll call this phi tilde, the generic potential that satisfies the constraints I've given is of this form. Now I can, for convenience, define a dimensionless variable phi by removing the tilde and taking the mass out. This mass is ordered gut mass. So the potential is of this form with higher order terms suppressed by the difference between the gut scale and the Planck scale. So similarly in a two-field case, I've got two fields phi and chi, which are also dimensionless, and the coefficients a and b, which appear these potentials, are dimensionless numbers. I'll take them to be order 1. This means all the terms are order 1 with respect to the gut scale. Okay, so the terms which are cubic can be either positive or negative. The terms which are quartic are positive to ensure boundedness of the potential. So I'll choose these coefficients from various distributions and see what happens. So I'm looking for the existence of minima, relative minima possibly, in this potential, such that slow roll conditions are satisfied. The slow roll conditions are essentially telling us the shape of the potential. So the first slow roll condition, which relates to epsilon, is a condition on the first derivative. The second slow roll condition is a condition on the second derivative. Now we know that inflation mimics the case in which the dynamics of the universe is governed by a cosmological constant. So the pressure equals minus the density. And that's ensured for us by taking the kinetic terms being much smaller than the potential term in Lagrangian set. So that's the origin of this condition, and the origin of the eta condition is basically a constraint on second derivatives that appear in the equations of motion. The measurement we've got is the spectral index. The spectral index is 0.9655 plus or minus 0.0062. We express the spectral index in terms of these parameters eta and epsilon. Now we express this in terms of the difference between 2 eta and 6 epsilon. So we assume that eta and epsilon are the same order, then in order to satisfy this constraint, we require that epsilon and eta are both roughly 10 to the minus 2. It could be there's some detailed cancellation, which gives us this without making this assumption. So what I'm going to do is I'm going to look at the relative minima for these potentials with random coefficients, and I'll ask how often are these slow roll conditions satisfied. So it turns out that for the single field case, there's a range of parameter space such that we can satisfy these slow roll conditions. But I'm not so worried about the single field case, as the data suggests the form of the potential I've shown you is unlikely at 2 or 3 sigma level. I'll focus on the multi-field case. So in the multi-field case, we basically do a numerical study with Mathematica. And there's a question of how do you choose the coefficients which appear in the potential. One choice is to take a window and just choose numbers randomly within this window. So if I take A, which can be positive or negative, to lie between -3 and 3, and B to lie between 0 and 5. And the reason I do this is I don't know the parameters a priori. So there's no natural condition to inform me of the shape of the distribution from which I should select these numbers. Another possibility is, well, there's a central limit theorem, and you have a bunch of coefficients in your potential. So maybe what you should do is you should take distributions that are consistent with the central limit theorem. Now we have a small number of potentials, a small number of parameters that define the potential, so we're probably somewhere between here and here. We're not really in a large range of parameters, so maybe the central limit theorem doesn't fully apply, but we may be better off than just choosing things uniformly. It turns out that the choice doesn't matter all that greatly. So since A can be negative or positive, I'll choose A from the Gaussian distribution, consistent with the central limit theorem, and I'll choose mean 0 and variance 1. If I'm looking at just positive numbers, the natural distribution to use is the gamma distribution, and I'll choose gamma with shape parameters k and theta to be set to 1. So when I do this and make choices using these distributions, what I find is that relative minima satisfy these slow roll conditions at roughly 0.1%. So I haven't included higher order constraints related, for example, to the third derivative of the potential, but there's nothing that stops me from doing that. And if the spectral index runs, that's something which we can implement fairly readily as well. What I haven't done so far is check how many e-foldings there are. And the reason I haven't done that is it requires me to put additional inputs in, namely initial conditions. Where do I start rolling? And how long do I roll within these minima which satisfy these low roll conditions? So that's something which we'll leave for future work to see how often we get sufficient exponential inflation to account for the large-scale structures that we see today. So the goal then is to import these ideas to string model building. So far, there have been a few examples of string constructions, mostly by the ICTP group, Bebedo, Chicoli, their collaborators, that try to take one of these large Swiss cheese geometries and see whether they can engineer inflation. Essentially, they often look at fiber inflation in these scenarios, where you consider some Calabi-Yau Toric threefold as K3 with some fiber on top, and you engineer inflation in that context. They have some models. But since we've got the largest current database of these Swiss cheese geometries with multiple large cycles, we want to see whether we can do things systematically on the geometries you've got, and this is work that's in progress. So far, I would say that heterodic model building for particle physics has generated for us semi-realistic models in the sense we've got the right matter spectrum, the right interactions. We just don't know certain parameters that appear in the Lagrangian. We don't even have that yet in a systematic way for these cosmological constructions. We're just starting out on that. So I'd like to see cosmology at the same level of realism as particle physics model building in these string constructions. So this is a shape of the potentials that I was looking at earlier. We see that they have certain, well, these are two sample potentials that satisfy these slow roll conditions. We see that there's some steep direction, and there's also some valley. We're looking to see whether this is a universal feature of the solutions we found. So the guys who did most of this work are Yan Xiao and Da Zhu. Luca was also on the paper, and Yang Gui He in London. So Yan and Da were Yang students. That's the main picture I was able to find of that. We're also trying to see whether we can start systematically probing these databases for the types of geometries that we have using big data techniques. So we're trying to see whether machine learning can tell us if we give the machine a data set which we train it on, can tell us whether a geometry is likely to be Swiss cheese or not. So we've started looking at this, and the various different ways of teaching a machine to analyze data. There are things. There's a methodology called supervised learning, in which you feed the machine whether some drug is effective in fighting cancer or something. And this is, for example, used in looking at clinical trials in applying this machine methodology. If it's unsupervised, just give it the data and you let it figure it out. And Google News, for example, for the recent programs to beat Go, use unsupervised learning. There's also a methodology called reinforcement learning, which involves a punishment reward system. You punish it when it fails, you reward it when it succeeds, and you try to maximize the reward. So what we have are essentially very rare properties in our data set. For example, we're looking to see when a geometry is Swiss cheese in a large database of Calabi-Yaus. And it's difficult to identify when you're successful with very rare properties. So what I mean is that suppose you've got a machine which tells you the answer is no every time you ask it a question. If that's right, if that's the correct answer 99.999% of the time, it's very difficult to distinguish that program's success rate from a program which says yes occasionally, sometimes correctly and sometimes falsely. So I've looked in the machine learning literature to see whether there are good metrics for testing whether a program is successful at finding a rare property within a data set. And the literature is very confusing to me, so I don't have a good answer to the question of how to judge the value of one of these programs. So that's where we are right now. So far, we've tried it. Naively, it looks like it hits correct results some of the time, and it fails some of the time. And we're trying to assess how good our programs are. But it seems that this, because we've got large data sets now in string theory, it seems these big data techniques may be a useful new tool to use in order to study aspects of string factorifications. Okay, so let me summarize. The results we found are there are patterns in the distribution of Hodge numbers associated with reflexive polytopes. And starting from these reflexive polytopes, we've begun to construct, using very old techniques, a database of explicit Calabi-Yau geometries that can be used for various different aspects of model building. Within this database of Calabi-Yau geometries, I've found new Swiss cheese solutions, and these new Swiss cheese solutions often have the property that there are multiple large cycles. The fact that there are multiple large cycles gives us flat directions of potential. These flat directions can help explain string constructions for inflationary cosmology. And to model how this might work, I looked at random landscapes. So far, we don't have a full analysis of the new Swiss cheese solutions we found and their efficacy for cosmology. So we've begun by just looking at random landscapes. We put in order 1 numbers into the potential and ask how often the relative minima satisfy inflationary constraints, and the most naive constraints get satisfied by 0.1% of the time. Now, since we've got this database, we want to use big data techniques maybe to assess when these rare properties are realized in this database, and the results so far here are inconclusive. I would like to see, so this is Switzerland. This is a landscape of Swiss cheese in Switzerland. There are different areas of Switzerland, different cantons with different kinds of cheese. And it might be that certain manifolds of Swiss cheese type are good for various things. So I'd like to see a description of the database of Calabi-Yau geometries and what string compactification of different geometries gives us. So this is still work in progress, but I hope that in the future we can report on what good sprints manifolds are, for example. So thank you very much.
We have some time for questions.
So maybe you mentioned, but if I understand all these numbers you gave for Calabi-Yau or for Toric,
That's right.
So is there some feeling of how big the subset of Toric is compared to the non-Toric case?
So there are 2 big databases that exist. One is a Toric database, and the other is a complete intersection database. So there's some overlap between the 2, but there are order of 5 geometries common to the 2. In general, the complete intersection database is much, much smaller. So order 10,000 threefolds maybe. So this is potentially order 500 million threefolds, or many more if different triangulations lead to different geometries. So the Toric database, Toric Calabi-Yau's, is the biggest database we've got of threefolds, and it's much, much bigger than intersections. We don't know about anything else really.
But is there really an expectation that the number is finite? 60 Calabi-Yau?
I don't know. Certainly the number of Calabi-Yaus you can obtain from a Toric type is finite.
Sure.
but I don't know whether there are infinite families, continuous families of Calabi-Yaus of non-Toric type.
What is the input data for that machine learning?
So basically, we take examples of Swiss cheese that we found. We feed it some subset of that, and then we see how it does on the Swiss cheese geometries we found that we don't tell it about.
But you give actual numbers, which character?
Yeah, we give the actual topological data, the Kähler cone, intersection numbers, everything we've got in our database for the geometries that turn out to be Swiss cheese.
And one big worry is if there is a bias for the feeding data, given the condition,
Yes.
it's easy to solve.
That's true. We haven't looked at the most general solutions that are, say, Swiss cheese. We've just looked at some subset in which the conditions on the intersection tensor, for example, are relatively easy to solve combinatorially, basically. So we haven't, that's certainly a worry that we're not looking for the most general case. Maybe the program can find these special cases that are less than general. Or maybe the program reports that something is Swiss cheese, and it turns out to be Swiss cheese because it's finding some patterns that we haven't found in the obvious way. That's certainly a possibility as well. So there are definitely caveats that one should keep in mind when you employ these machine learning techniques.
Right, if there are no further questions, let's thank Vishnu again. And then just a reminder again that checkout for those who are